Okay, so I'm continuing from where I left off, more or less. And so this is the theorem I want to prove, that I've got two graphs x and y. And now I'm looking at subsets of the Cartesian product of Vx cross Vy. Now, I need at some point to remark that any subset of Vx cross Vy is by definition a relation, okay, on x and y. But so anyway, but I'm not worried too much about that. So we've got a subset S of Vx cross Vy, and I'm trying to decide when it's the graph of a homomorphism. Now, the graph of a function consists of a function f consists of the ordered pairs x comma fx as x runs over the domain. Okay, so that is the graph of a function. Okay, and so if that function happens to be a graph homomorphism, well, it's still a graph. Okay, so the word graph is getting used in two completely different meanings, and there's not much we can do about it. So the statement is that a subset S of the vertices is the graph of homomorphism, an induced subgraph of x of size S to y, if only if it's a co-clique in the homomorphic product x, whatever that is, y. So the point is, this is a graph that we can construct. I'll remind you again what it is in a moment. This is a graph we construct, and the co-cliques in there of size S give us homomorphisms of some subgraphs of x to y. Okay, and so it translates the problem of finding a homomorphism into the problem of finding a co-clique. Now, I did an example in the last lecture just dealing with colorings. So there I was worried about homomorphisms to Kn, but now I'm doing a more general problem. Now, as I said before, this is due to Hal and Neshatril, and well, I can never, some people like to distinguish between the size of a graph and the order of the graph, and I can never keep the two things straight. But in this context, size is just number of vertices. Okay. So the corollary of the proof is that if there's a homomorphism x to y, if only if the size of the largest co-clique in the homomorphic product x and y is the equal number of vertices in x. Okay, and so that's the well, that's the if you take y to be Kn, that's the result I mentioned earlier. Now, just to remind you what this graph is. So there is a definition which I've written there in blue, and that hasn't changed, but you can also write it out in terms of adjacency matrices, which is, I think, easier. So it's the adjacency matrix of the Cartesian product of x with the complete graph on the vertex set of y. So it's just a complete graph. I'm just using y because I don't know what the number of vertices in y is, and I don't want to set aside a letter. And then I've got the adjacency matrix of the direct product x times the complement of y. Now, just remarking, if y is regular, then you can actually determine the spectrum of this in terms of the spectrum of x and the spectrum of y. Although as far as I know, nobody's looked into using that to get anything. I think I played a little bit once, and it's not easy to get useful bounds. You get bounds, but they're not being tight. Okay, so this is our graph. So the rule is, well, there's the definition in terms of matrices. The second definition is two vertices are adjacent in the homomorphic product if the first coordinates are equal, or the first coordinates are adjacent and the second coordinates are not. Okay. Now, if you can remember that, good for you. I'm not sure how we're on to. So we want to prove that the homomorphisms from a subgraph of x to y correspond to co-cliques. Okay, so of the right size. So suppose f is a homomorphism from an induced subgraph x0 of x to y. Now, if u and g are adjacent vertices in x0, then their images are adjacent in y because f is a homomorphism. Okay, so they're adjacent, and so they're still adjacent. And so it follows then, since the first coordinate's not adjacent, the only way these two things could be adjacent, it would be if fu was not equal to f, not adjacent to fv, but it is because f's homomorphism. So there we have an easy argument telling us that if f is a homomorphism, okay, then the vertices x comma f of x give you a co-clique in the, well, they're a co-clique in this graph and a co-clique in that graph, and therefore a co-clique in the sum. Okay. Now the converse is a little bit more work, not much. The issue is that if you understand the example with showing relating chromatic number to size of coke leaks, then it's not a very big step to think about, well, can we do something more general? And once you start thinking about a second, there's sort of only one way of doing it, and it works fairly straightforward. So for the converse, we're assuming I've got a subset of the vertices of X cross Y, and there's a coke leak in both the graphs, Cartesian product of X with a complete graph, and the direct product of X with the complement of Y. And so now we define the domain D of S. Now this domain is, we're building up a function. So this domain, as it means what it usually means, but we're going to find a set of vertices in X such that X, Y, X comma Y is an S to some Y in Vx. Okay. So the things that get mapped to something, these are the things that get mapped to something in Vy. Okay. So that's our definition of domain. Now the claim is if U is in the domain and Y and Z are vertices in Y, then Uy and Uz are adjacent vertices in the Cartesian product here. So this tells us if U is in ds, there is exactly one vertex Y such that xy is in S. So that tells us that now that S is not just the graph of some relation, it's actually a graph of a function. Each vertex in X gets getting mapped to one point in Y and not two or more. Okay, so it's a graph of a function from its domain to the vertex of Y. Okay. And so so the point we define the domain, okay, a little bit hard to keep that straight, and then we claim that the S is giving us a function from the domain into Y. So the thing left to do is to show that this function is a homomorphism, and that's what we're doing here. So so I'm calling my function G, and so G is a homomorphism. Now, if U comma Y and V comma Z are two vertices in S, and U is adjacent to V in X, then since S is a coke leak in this graph, Y is not equal to Z. Okay, and since these graphs are not adjacent in the direct product here, we have Y is adjacent to Z, so therefore G is a homomorphism. Okay, so that's the argument. Okay, so we can extend the relation between, so we can show that we can reduce finding homomorphisms to finding coke leaks, which is interesting. It's not terribly practical, since finding coke leaks is then be hard, but well, that's what it is. Now, there's a lemma due to Robinson and Manchester and Robertson. Actually, it first appears in his thesis, and that just tells us that there's a quantum homomorphism from X to Y, if and only if alpha Q, the size of a quantum coke leak in the homomorphic product of X to Y, is equal to the number of vertices of X. Now, so this is just the previous theorem with Q added twice. Once on the homomorphism, once on the alpha. Now, the proof in Robinson's thesis takes a couple of pages and makes heavy use of quantum games. And so I got no intention going through it. But there it is. So we have this analog holds. And so this is a nice result. And as I said, the proof is complicated. Proof is quite complicated. And there's no way I'm going to try and do it in a Zoom lecture. Now, a corollary of this is that if there's a quantum homomorphism from X to Y, but no homomorphism from X to Y, then the coke leak number of the homomorphic product is less than the coke leak, the coke leak number of the homomorphic product is less than the quantum clique number in the homomorphic product. So what this is telling us, if we have examples of graphs that are quantum isomorphic but not isomorphic, then we're going to get examples of where alpha and alpha Q are different. And at this point, we're trying to understand these quantum parameters, and so, what's the first question is, well, when do they disagree and when do they agree? And what this is telling us is a relation between when things break down on the homomorphism level and when things break down on the coke leak level. Any questions at this point? Now, we saw an inertia bound on alpha of X some time back. And so the interesting thing is that this inertia bound is also it's an upper bound on alpha, the minimum of the number of non-positive and not number of non-positive and number of non-negative eigenvalues, but it's also an upper bound on alpha Q. And so this is we saw that for the chromatic number that the Hoffman bound was a bound both on the chromatic number and on the quantum chromatic number, which is a stronger statement. And the same thing is happening here with alpha. And I find this very interesting because these bounds worked out by Hoffman, well, 50 years ago. I mean, there was no thought of anything quantum at the point. There were bounds on parameters of interest. Okay, and yet it turns out they're not, in a sense, not bounding what we thought they were. They're bounding quantum co-cliques rather than co-cliques. And so I still find that very intriguing. What's going on here? So I'm going to sketch the proof of this. So the nice thing about the inertia bound is that it's very easy to deal with the weighted case. What's going on? And that's a strong result. So we'll talk about the weighted case. So the claim is that we have an emission weighted adjacency matrix for X. Okay. So it's zero whenever the IJ entry is zero whenever I is not equal to J and it's emission. Then the quantum co-clique number is bounded by the number of non-negative and the number of non-positive eigenvalues. So same bound as before. Okay. And so this is a strengthening of the inertia bound on the sides of co-cliques. Okay, now the proof involves us bringing in one more parameter, unfortunately. So, and that's a projective packing. So a d-dimensional projective packing of a graph is an isomorphism from the graph to the orthogonality graph on the d by d projections. Okay, so d by d projection. So you've got it's an infinite graph, and so okay, so it's an orthogonality graph. Now, so that's it. So we've defined the first sentence there defines a projective packing. The question is we want to assign the value, and so if psi is such a homomorphism, its value is 1 over d times the sum of the rank of the images. So you're mapping your vertices to projections, you sum the ranks and then divide by d, and the projections are all d by d. We're not assuming that the projections have the same rank. If the projections had the same rank, I would be talking about Grassmann's again, because the Grassmann graph is the orthogonality graph on projection d by d projections of rank r for some r. But we're dropping the restriction on the rank can be whatever it wants to be. Okay, so that's the value of a projective packing. And then the projective packing number is the supremum of the values of the projective packings of X. And just to make things confusing, it's noted by alpha sub P of X. Okay. I started lives of group theory, so P is always a prime, so I don't like that very much. And Q is a prime power, but we won't go there. I want to remind you the definition of quantum co-clique. So it's a matrix with quantum co-clique in X is a matrix with rows indexed by X, S columns, and the entries are projections that satisfy these two conditions, so that the column sums are the identity, and that the product of two entries PUI and PVJ is 0 if U and V are equal, so any two entries in the same row are orthogonal, or if U and V are adjacent. Now, there's a couple of things that aren't easy. You have to think for a while to see that what happens if I take D equal, does this generalize the classical definition of co-clique? Okay, it does, but to take some thought. Okay, so there's that. The second thing is, is this indeed a quantum co-clique? Our definition of a quantum clique is that it's given by a homomorphism of Kn into our graph, by a quantum homomorphism of the complete graph into our target graph. Okay, satisfying certain conditions, and then they said a quantum co-clique is just you're just taking a homomorphism from the clique into the complement. Okay, and this doesn't look like that, but we're not going to go through every detail. So there are a few things there, but we're going to take this on trust that these two conditions, which are fairly simple, describe quantum co-cliques. Okay, so it's the vertices of X times S matrix. The entries in each column are under the identity, so they're pairwise orthogonal, and the vertices projections corresponding to pairs UI Vj, 0 if U is equal to V or U is adjacent to V. Okay, so that's the definition. And then, well, we need a preliminary limit, namely that we're going to get the claim is that the projective packing number is a lower bound on the quantum co-clique number. Okay, now, okay, so let's do that. So we're going to start with the quantum co-clique. So it's a set of projections. Okay, and now we're taking the row sums of this matrix of projections. Okay, now the column sum is sum to ID in this case. The row sums are just pairwise orthogonal projections. So the sum of a row is a projection, and its rank is at most D, but we don't know more than that. Okay, so we get a projection, and the projection on the U row we're going to call P sub U. No reason to be imaginative. Now, these sums are orthogonal projections, and you can check that when you take the inner product of PU with PV, well, I've written it out here. So there's two parts I equal to like this. And if you stare at these two parts, you see they're both 0. So these guys are orthogonal in that sense. So when I'm talking about orthogonal projections here, I mean they're orthogonal as projections. This is again confusing. I mean they're orthogonal as projections, so they're D by D in emission and idempotent. Now, what we're establishing here is they're also orthogonal in the other sense of the word. And I guess I'm using graph twice. You can't complain that I use orthogonal twice, but this is more completely standard, unfortunately. So then we work out some of the ranks of those projections. P sub U is D times S. And so it follows that the projective packing number is less than or equal to the quantum chromatic number. Okay, so the proof of the inertia bound, we're going to work with the packing number. So Godsil and Elphick produced a proof of this ratio bound. Now, there are some sense 3 proofs of the ratio bound. The first is Spetkovich's proof, to which use interlacing, and it's quite simple. The second is that I gave a proof using this. I looked at the span of the eigenvalues with the eigenvectors with positive eigenvalues and the space spanned by the eigenvectors of negative eigenvalues, and then observed that there was a co-clique. It gave us some space which had to fit near these things, but be disjoint from it. And from that, we got the bound. Now, there's a third approach, which I'm sketching here. It's really related to the second one, but the first glance it looks different. And so I'll explain that. So we're starting with a emission-weighted adjacency matrix for our graph. Now, okay, so first mistake. I got my A's and W's back to front here. And so I'm going to look at the vectors X such that X star WX is 0. Now we're working in complex space, doesn't really matter. This is emission. The vectors actually, basically here I'm working projective space, but I'm going to lie and pretend that I'm not. Okay, so technically so the argument is that this set of points is giving me a projective quadric. Okay, it gives you a quadric in a complex vector space. Okay, and it's a question whether you want to work with the vectors X or with the lines that they span. And in this context, it's a little bit better to work with lines. Now, in any case, so we have this set of points, and I'm calling it a projective quadric, and a subspace of C to the n is isotropic if x u star wv is 0 for all u and v in u. So in the previous proof I gave you, I had that subspace spanned by the vectors E sub x for x in the Cochlear S. And I did basically prove that subspace was isotropic, but didn't use the words. So this is sort of how a geometer would look at it. So well, I'm saying this again here. If S is a Cochlear, then the span of these vectors, this span is an isotropic subspace. Okay. Now the point is, the geometers tell us that the dimension of the isotropic subspace is going to be bounded by the number of non-positive and number of non-negative eigenvalues of the matrix. In fact, the triple with the number of positive eigenvalues, the number of zero eigenvalues, and the number of negative eigenvalues is called the inertia of the matrix. So it's a triple of numbers to sum up to the number of vertices. Okay, and so this is all standard in the right place. Now I wanted to try and do a picture. So a hyperbolic quadric, the simplest hyperbolic quadric is to mention two rings, one above the other, and joined by strings. So the bottom ring is just hanging vertically. So you say, oh, it's just a cylinder. Well, a cylinder is kind of a flat quadric. To get an actual quadric, you just twist the top through a certain angle. And so now you've got, and so when you look at the shape, so if you imagine there were lots of lines, when you look at the shape, when you twist, you see a smooth surface. It's a quadric. Now, one thing you then see is on that smooth surface, the strings I had here are still on the quadric, so they're lines on the quadric. And this is something for, you generally think about surfaces, you don't think about them containing subspaces, but they generally do. And so if I take the top by an angle alpha, then I'm going to get lines through which I'm going to have my hyperbolic quadric partitioned into lines. Now, if I rotate the top through an angle minus alpha, I'll get the same quadric. I get a second set of lines. So the conclusion geometrically is there are two sets of lines through each point. There are two lines through each point on the quadric. Now these lines, each of these lines is an isotropic subspace. Okay, and so what I'm giving you here is examples of an isotropic subspace on the surface. Okay, the conclusion is that if we have an isotropic subspace, it's bounded by the number of non-positive and number of non-negative eigenvalues of the matrix defining the quadric. And so that's exactly what I just written here. And so we turn to the proof of the theorem. And I'm going to basically wave my hands about this one. I don't think it's so it's a similar trick to, we defined P sub u to be the row sum, and we recall its projection. And now we're going to take it. So P sub u is a projection, but we can take an orthonormal basis for its column space. And so we've used this crazy notation, psi sub u comma I, where I goes from 1 to the rank. Okay, and so so we've got those vectors, and then we define this second family of vectors, tensor products of the standard basis vectors with columns. Okay, and then the claim is, and what I've got written here purports to prove, that those vectors span an isotropic subspace. And so that gives us a bound, and that reduces to the upper bound on the projective factor number. Now, do I have, oh, I'll go to it now. Now, the inertia bound has been around for a long time, probably much about the same amount of time as the ratio bound. And at first, I think it was appreciated how useful it was in terms of weighted, the fact you work well with weighted matrices. And so the question then is, for which graphs is it true that there's a weighted adjacency matrix such that the inertia bound is equal to the size of the independent set? Now, from my point of view, there's very little reason to assume that is true, but it was verified by some other people on the computer that it is actually true for graphs up to about 10 or 11 vertices. So actually, that's a lot of graphs. I still wouldn't be prepared to change my tune. Eventually, John Sinkovic, who was here on a postdoc, proved that the Paley graph on 17 points, on 17 vertices, that's the graph on the field of order 17, 2 vertices adjacent if the difference is a square. So that was an example where the weighted inertia bound was not tight. And with a URA here, he found more examples. But now it follows from the quantum stuff that whenever you get an example where alpha x is less than alpha q, then you're going to have examples where the weighted inertia bound is not tight. Okay, so that was kind of interesting. Okay, now last thing I'm going to do is I'm going to give you the recipe for a graph where alpha and alpha q are different. Although at this point, I'm not going to prove they're different. The construction's due to Peter Vassan from her PhD thesis. And the graph we want is a Cayley graph, and it's not too big. So we take the set of elements of order 2 in the symmetric group on 4 letters. And so there are 6 transpositions, and there's 3 double transpositions, so you get 9, a set of size 9. Okay, and so you get a Cayley graph, which is going to be a 9 regular graph on 24 vertices. And then the claim is that alpha of x, maximum size of Kochlik is 5. Now, there's no particular problem verifying that. You just stuff it on the computer, and you get that very quickly. So you know that alpha is equal to 5. And if you've got the time and you're sufficiently dedicated, you can probably come up with a direct proof. But I'm happy with being told that you put in the computer said it was 5. Now, the other comment is that the quantum Kochlik number is 6, so this gives us a separation. Now, there are other examples, but the list of examples is fairly short. Make a few comments about it. The permutations, well, there's 4 permutations here, including the identity. They form a subgroup of order 4. The symmetric group on 4 letters has got a subgroup of order 4, exponent 2, that's this guy. And certainly these guys, since these things are in the connection set, actually you want to do a calculation, but you can verify this is actually a Kochlik of size 4. So you've got a subgroup which is a Kochlik of size 4. But now this subgroup of order 4 has got 6 cosets, each of order 4, and each of those cosets will be a Kochlik. So you've got this clique structure of 6 cliques of size 4. And given that it's not too hard to show by hand that alpha of x is most 5. Now, to show that the alpha q of x is 6, I have to come back and write down the matrix I need for a quantum Kochlik. And I think I'm going to have a sneaky argument for do it later on after I start talking about quantum isomorphism. So I'm not going to do that right now. But so this is the graph. And the issue is to prove that alpha q of x is 6. And one point of this is that the computer doesn't help us. Maybe there are ways of doing it. We don't have any code which would actually produce a convince us of this. Okay, so we'll leave it at that for now. Yeah. Okay. So what's the time? This is wrong for some reason. Okay. So that's quantum Kochliks. Oh, we can get one step more. So I want to start talking about quantum isomorphisms. There are various wrinkles in this. One thing you need to remind yourself from time to time is that a quantum homomorphism is not a function from the vertices of the first graph to the vertices of the second graph. It is not defined as a function. Okay, and if you have a quantum homomorphism from one graph to another, there's no way to call it phi. There's no way to assign a many to phi of a vertex. Now, maybe there should be something you think, well, I'm not really going to argue, but the point is you are not dealing with functions. technically you're dealing with relations, you can compose relations and everything works. So it's just a warning from time to time. If things get confusing, you may have to remind yourself, this is a quantum homomorphism, it's not a function. If you have a quantum homomorphism from X to Y, you get a function from X into the measurement graph of Y, but that's infinite. Okay, and when you compose homomorphisms, you don't work through the measurement graphs. Okay, anyway, we're going to talk about so I want to talk about quantum isomorphisms. So I want to start with the n colorings of Kn. So if you have a complete graph Kn, the number of n colorings of that graph is n factorial. So in fact, every permutation of the symmetry group on n letters is an n coloring of Kn. Okay, and so you can write these. You can write out permutations as n by n permutation matrices. Each row in column sums to 1, and the permutation matrix is unitary. Okay. Now so the next question is to think about quantum homomorphisms from Kn to Kn. Okay, so now you're going to have d by d projections. Each row sums to the identity, and each column sums to the identity, because the things, if you have two vertices of a plate graph X, they're adjacent, and if they're in the same column, they're being mapped to the same vertex, that forces those projections to be orthogonal. So a quantum n coloring of Kn is given by an nd by nd matrix of projections, where each row sums to ID and each column sums to ID. And when d equals 1, this is just the usual coloring, but described in a more complicated way. Okay, so we're going to define a quantum permutation to be an n by n matrix of d by d projections, such that all row and column sums equal the d by d identity. Okay, now this is reasonably straightforward, and it is motivated a bit by what I've said here about the relation to classical colorings. You will notice that I have not set, the question I'm not answering is, when is a quantum homomorphism an isomorphism? In fact, I can't even answer the question when is a quantum homomorphism a surjection. As stated, that makes no sense, but there is a replacement for it in categorical terms. So there are lots of things we can't answer. Now, we can show that a quantum permutation is a quantum homomorphism, but we won't go there right now. So the point is, we're defining a quantum permutation to be these n by n matrices, and basically a quantum automorphism is going to be a quantum permutation which commutes with the matrix adjacency matrix tensor ID. So we're going to have a definition of a quantum automorphism. And then we go in our final merry way. Now, unfortunately, there are two definitions of quantum isomorphism, and what I've given you is the so-called tensor product version. There's a more complicated version using C-star algebras, and the two definitions are inequivalent. And in both, so there are two notions of quantum isomorphism. The question of whether two graphs are quantum isomorphic is undecidable in either form. Okay, but all I'm remarking here is that there's a couple of definitions of quantum isomorphism. We're dealing with one which is called the tensor product version, which is a little simpler. Okay, and we can't answer many obvious questions in that case, so there's not much advantage looking for the more complicated case at this point. Okay, but really, I just want to warn you: there are two definitions of quantum isomorphism, okay, which differ slightly, and I'm dealing with the one I've just given you. Okay, so there's nothing wrong with what I would have given you. It's just there is some other stuff there. Now, to understand quantum isomorphisms and automorphisms, I need to go back and talk about coherent algebras. And I discussed coherent algebras much earlier in the course, and so you've had a lot of time to forget it, and you probably wanted to suppress memory anyway. But at one point I was talking about transitive permutation groups and orbitals, and I threatened you with coherent algebras, and now they come back and we have to pay attention to them. What I'm calling a quantum permutation, I should say, I don't quite know what's at this point. They're sometimes called magic unitaries. It's more useful to call them, and some versions of them are called quantum lattice squares, but so there are other names around. That's only naming, so but quantum permutation is quite standard. And the first thing is that a quantum permutation, we're viewing it as an ND by ND matrix over the complex numbers. It is unitary, and it commutes with the all ones matrix. Now, this is just a statement of properties of a matrix for D by D projections whose rows and columns sum to the identity, to ID. And so this is, the second claim is very easy, or both claims are easy, and so I'm going to make them as exercises. So the matrix, the ND by ND matrix over the complex numbers is unitary, and it, well, actually it probably commutes with J tensor ID. Yeah. The other comment, and again, is that the matrices that commute with a quantum permutation is a coherent algebra. Now we're proving that shortly. Okay, yeah, what have I done? No, sorry, I got it off. So if P and Q are quantum permutations with indexes D and E respectively, then their co-product is a quantum permutation index DE, and their sum is a quantum permutation of index D plus E. And again, I'm making that as exercises. There's nothing to be, okay. Now, we say that an n by n quantum permutation matrix commutes with an n by n matrix M. Now, here we've got a quantum permutation matrix, whoops. And generally, I think of them as n by n matrices over some algebra of D by D matrices. So the matrices over a ring, and that ring is D by D matrices, okay? If I'm thinking it as an ND by ND matrix, as I did just here, then I'll warn you, okay? It's, the definition of the quantum permutation matrix commutes with the matrix M over C if this is true. Don't want to do that. So it's not that P commutes with M, P commutes with M, the tensor ID. And that's why I had to change J to J tensor ID up above. So, and so you're taking a bigger matrix, okay, and never commutes with that. So that's the definition. That's, we can define quantum isomorphism, and I'll come back to that later on. But so there's no particular difficulties with the definition as such. I mean, trying to find quantum isomorphisms is another question, but we'll come back to that too. Now, the theorem is that the set of n by n matrices that commute with a quantum permutation forms a coherent algebra. And it contains a coherent algebra generated by A, but I'll come back to that. Now, what's it mean to be a coherent algebra? Well, it means you're a matrix algebra. You contain I and J, and you're closed under Schur product. Now, one reason this theorem is interesting is if you have some permutation matrices, n by n, then the n by n matrices M, which commute with those permutation matrices, they form an algebra because M commutes with all these permutations and N does, so does their product. But you can also show that the Schur product, M circle N, commutes with all those matrices. So if M commutes with P and N commutes with P, then their Schur product commutes with P. And so the commutant of a set of permutation matrices is a coherent algebra. Okay. Now, what this result is telling us is, well, actually, we don't have to deal with just ordinary plain old-fashioned permutations. We can deal with quantum permutations. The result is still true. Okay. Now, then a bit of jargon. So This last sentence makes no sense. Let's just take it off. Come back to that. Nope. Yeah. And so now I'll just repeat some of what I just said. A coherent algebra is an algebra in invariant matrices such that C is closed under transpose and complex conjugation. It contains J and it's closed under the Schur product. So J is the identity with respect to the Schur product. Now, by my definition, every algebra contains the identity, and every mapping homomorphism between algebras maps identity to identity. Well, I just make it explicit. So I know the identity is in there because that follows from what how I define the algebra. But it's closed under the Schur product, and that's a crucial property. Now, the simplest example is simply to take the identity matrix and the all ones matrix and take their span. Okay, that gives you an algebra of dimension 2. It's closed under matrix multiplication. It's closed under Schur multiplication. It contains J, blah, blah, blah. So there you are. There's a two-dimensional coherent algebra. In fact, it's the only two-dimensional coherent algebra. For a slightly more complicated example, maybe take the adjacency matrix from your graph. So in this case, I'm going to take three matrices: the identity, the adjacency matrix, and the adjacency matrix of complement. Now note that the Schur product of any two of those matrices is 0. So if I take that set and adjoin 0 to it, then those four matrices form a set which is closed under Schur multiplication. And so it follows that the algebra generated by these matrices is closed under Schur multiplication. You can see this in other ways. So this span is a coherent algebra. Now, this coherent algebra, and this one too, has got nice property of being commutative, because for a regular graph A and J commute. That's nice. It's generally not the case, but we take advantage of it when it's there. This, and I've got another class of examples which is no longer commutative. Just take the algebra of n by n matrices. Okay, its algebra is an algebra dimension n squared. This is the maximum possible. It's closed on the Schur product. It's closed on matrix product. Contains everything you want. And in fact, whoops. Every coherent algebra we deal with will be sitting inside this as a subalgebra. Now, subalgebra as a coherent algebra is be an algebra of matrices closed under Schur product containing I and J. Okay, and closed under the complex conjugate. And so the theorem is that the commutant of a set of n by n permutation matrices is a coherent algebra. Now, you don't need to go back and understand all this stuff I just did about defining coherent algebra and giving you the examples. What you really need to do is to prove that this guy is Schur closed. Everything else will follow. Okay. And there's a fairly short proof. So I'm assuming a bit of a inversion first. I'm claiming if I've got two coherent algebras, subalgebras of n by n matrices, their intersection is also a coherent algebra. Okay. That's the usual intersection of subspaces of vector spaces, subspace intersection of subgroups, a group is a group, all these things. So the point about this is I said that any commutant of a set of n by n permutation matrix. I'm doing the I'm myself confused. So the commutant set of n by n permutation is a coherent algebra. Okay, the point I'm trying to make is that we only need to worry about the case where our set's got size 1, because if we can prove that the commutant of a single permutation is coherent, then the commutant of a set of permutations is an intersection of coherent algebras and is therefore a coherent algebra. So you only need to deal with one. Okay, so that's nice. Now the proof in this case is we just assume we've got two matrices in the commutative of phi. So I commute with this permutation. Then I just compute P of M circle N. And you think about this for a second, that P of M circle N is actually equal to P applied to M circle P applied to N. You're just shuffling the rows of P, of M and N. Now, since M is in the commutative of P, I can move place MP by PM by MP and ditto for this. And so this is MNP. And so this is the proof. Now, as I said, this is the proof for plain old-fashioned permutations. And it's a useful result in its own right, but we're going for bigger fruit. What's the time? Yeah, I'll try. So, okay. Do I want to? So I'm going to prove the quantum permutation analog of that eventually. But I want to do, actually, yeah, this will work better. I want to prove a very important property of coherent algebras. The point is, we're dealing with coherent algebras over the complex numbers, or maybe the reals, doesn't really matter. And so it's an algebra, it's a vector space, so it has bases. Now, the claim is that there's always a basis of 0, 1 matrices. And these 0, 1 matrices are sure orthogonal. They show a product of different matrices is 0, and they sum to the all ones matrix. And this basis is unique. So there's a canonical basis of 0, 1 matrices that sum to J. Okay, so not only is there, there's a basis because this is just a vector space, but there's a basis of 0, 1 matrices. And so this is what makes coherent algebras combinatorial, because this basis is consisting of 0, 1 matrices. So you can view these as directed graphs. And so every coherent algebra is giving you, in a reasonably natural way, a collection of directed graphs. And the idea here is it's not too difficult. We define the case Schur power of a matrix to just the product of M with a Schur product of self M times. And if we have a polynomial, plain old-fashioned polynomial A of T, we define A circle M to be the corresponding thing with Schur powers of M in place of ordinary powers. Now we call this a Schur polynomial in M. Okay, it's a linear combination of Schur powers. Now suppose you've got a coherent algebra and you've got a matrix M in your coherent algebra. It's got distinct entries, U1 through UD. Actually, the simplest case at the moment, just imagine there are 2 entries, and let's be lazy and assume they're 1 and 2. So pick the polynomial which is a quadratic polynomial whose value on 1 is 0 and whose value on 2 is 1. So that gives me a quadratic polynomial, call it Q of T. Then the Schur polynomial Q circle that matrix is take my original matrix, replace the 1s by 0s and the 2s by 1s, so I get a 0, 1 matrix. So my point is, if I'm given a matrix with D distinct entries, I find a polynomial of degree D, which maps D minus 1 of the entries to 0 and the remaining entry to 1. And then if that polynomial is P, then P circle M will be a 0, 1 matrix. Now, since it's a Schur polynomial, since it's a linear combination of Schur powers, that matrix is in the coherent algebra. And so you can write every matrix in the coherent algebra as a linear combination of 0, 1 matrices. Okay. Now to get a basis, you've got to observe, well, yes, but if I have 2 of these 0, 1 matrices, their Schur product is also there. If that's non-zero, well, that's another 0, 1 matrix. So what you want are the minimal 0, 1 matrices in the algebra. And they form a basis for the algebra. And they're unique. If you agree on some way of ordering 0, 1 matrices, then you can argue that this basis is unique. And so you have a collection of directed graphs determining the coherent algebra. So I believe it's in the, I've written out what I've just said. I'm not going to go through it now. What's the time? Yeah, there's a couple of let's leave that for next time. So you know just where I'm finishing. Okay, so we'll continue with the continuing algebras in the next lecture. Any questions?